Thank you to everyone for joining us for this week's Power Hour on critical environment, airflow controls, and lab valves. We're joined by Auri. He is with Titus talking about their product offering. Just a couple of housekeeping items. If you have any questions, as always, please put it in the chat. We'll do our best to moderate. We may hold it to the end. We may interrupt Auri and ask him the question on the fly. As always, this will also be recorded and posted on YouTube, hopefully within the next few days. And this will actually lead into next week's presentation as well with our GreenHeck Lab exhaust fans, our vector fans specifically. So with that, Auri, take it away.
All right, thank you, Chris. Thank you very much. Pleasure and an honor to be here. My name is Auri. I am with Titus. I've been in the industry for critical environments about 6 years, so I'm just kind of starting to learn what's what. And I am hoping to share some of that knowledge with you all here today. So I started with Triatech in 2016. The history of Triatech is a pretty long one. They've been around since 1985. And the recent most exciting development was that they have been moved under Titus, still, which is part of Johnson Controls, but now managed and owned by Titus, which is great because they do air, they do what we need them to do. So when we talk about critical environments, there's a lot of different specific applications that cover this market. And this market cuts across several verticals: healthcare, higher ed, pharma, and sometimes even industrial. So you can see the various different applications that fall under this umbrella. Now, when we look at the critical environments specification landscape, specifically in North America, it's a little bit broken, if you ask me, because Division 23 is where we typically pull in the valves for the labs. Division 11 is where we see the fume hoods for the labs. And Division 25 is sometimes where we see the controls. So you have this really interesting master format spec in the industry where critical environments has become known as the tweener. It's in between, and bits and pieces of it in different divisions, which makes it a very niche-y specialty kind of go-to-market strategy. We are based out of Norcross, Georgia. That's where we make our air valves. That's where we have our functional demo rooms, test labs, and manufacturing calibration setups that you see here. And we're going to start with our product overview. So the way I think about critical environments is we're using the same ingredients to create solutions across a broad spectrum of requirements. So at the end of the day, I'm using the same components, the same control, the same air valves, but I am customizing their mix for the specific application needs that I have. So some might require 3 monitors, some might require no monitors, and so on and so on. So starting first, we have our FMS 2000C, which is our room level controller, the room brain. We have the FMS 2000M, which is a monitor only, put it at the door and forget it, to give you a pressure reading across the space. Then you have your central monitoring station, which is typically a nurse's station. We can display up to 8 parameters from either 8 different rooms or from 1 room. Finally, we have our fume hood controller, the HMS 1655, which is slated to get a display update exactly like these. So look out for that coming January 2025 is what I'm being told. Then we have our air valves. We have our Venturi air valve upgrade kit to get rid of the old pneumatic controls and put electronics and digital controls on them. And then we have a line of high efficiency fume hoods, which we're going to talk about at the end. So starting with some of the more basic application of critical environments is, of course, our operating suite, the most critical room in the hospital. That's where patients are open, exposed to the ambient conditions in the space. And that's why we want premium, pristine, clean air being pumped and dumped into that space and pushing all the potential debris and any contaminants in the air into the adjacent spaces, through the door cracks, through the drop ceilings and whatnot, so that nothing can land on the patient. Typically, what this image is showing here is this elaborate array of air curtains and skirts just around the operating table. Here I'm showing a simple supply and a simple exhaust for a dual pair lab or operating suite control of the pressure in the space. Now, on the far end of the spectrum, I'm going to call this the complex laboratory. A complex laboratory is anything that has more than one fume hood, more than one entryway, or some elaborate control sequences that require occupancy or setback modes. In this example, I'm showing 4 individual fume hoods. Each fume hood is like a mini room in itself. It's got its own workspace. It's got its own air change requirements in its workspace, and it's got its own dedicated fume hood controller to manage all of those requirements. And all of this is done for safety, right? The number one priority here is safety of the user. In order to make sure the fume hood is safe, we have an individual fume hood control on each fume hood. Each fume hood has its own exhaust air valve. The brown is a heresite phenolic coating to prevent corrosion from any chemicals that are being mixed or used inside of the fume hood. And now that I have 4 fume hoods and I know there are 4 CFMs being exhausted, I can do a total CFM exhaust and a total CFM supply into the space, and now I can balance the room. So in this scenario, the way we think about pressure control is that the fume hood is most negative, and it's got to be negative to the room so nothing can escape the fume hood work area into the lab zone. And if it did, the room is negative to the adjacent spaces like the hallway, so that nothing would escape from the lab into adjacent room, grow a pair of legs, run off to the local market, and cause a national pandemic, right? We just don't want that. It's bad for business. This is a real world scenario of what we typically see in a building. You'll have a mix of the spaces that we just discovered, throw in with some regular waiting areas and receptions. Now, it's important to note that Venturi air valves are the go-to for precision airflow control in these critical spaces like an OR, a lab, or a patient isolation room with some contagious disease. But when it comes to a regular waiting area or reception where we're only doing comfort control for temperature and air changes, where speed of response and accuracy is not so critical, regular VAV box applications is what is typically used. When it comes to room pressure controls, there's 3 types of room pressure controls. First one is direct pressure control, where we're controlling to a pressure set point. The second one is volumetric offset, where we're just using the supply and exhaust differential into a space, and we're trusting that the valves are accurate and doing the thing. And the last one is what they call sometimes cascade or progressive or VOC with pressure override. And it's basically the combination of the two, which gives you the best of both worlds. Now, the only drawback to that is your control sequence of operations becomes really complex and requires a certain level of skill and ability to execute successfully out in the field. Most of the time, VOC is most commonly used because that's probably the easiest cookie cutter approach to room pressure controls. And it's great for large spaces where there's a lot of traffic, a lot of doorways, a lot of fume hoods. Any dynamic air disturbances, VOC is going to be a better way to respond to prevent nuisance alarms. Direct pressure control is great for small, tight spaces like ORs and patient isolation room, where it's super critical to know if there's any change in containment instantly. So any alarms in a pressure control room should be taken seriously immediately. VOC nuisance alarms are typical because they didn't close the door, or they're standing in the door open and the timers trip out and cause a nuisance alarm like, hey, close the door, it's not safe. When we look at volumetric offset controls, we have a basic kind of a setup here with a supply valve, reheat coil, duct temperature sensor, and we have a general exhaust air valve that is controlling for 900 CFM exhaust and 1,000 CFM supply. Now, supply will typically modulate for temperature because the reheat coil's on the supply side. The general exhaust, in this case, will modulate for pressure and air changes per hour. In this specific application, we have 100 CFM positive offset. This means it's a positive isolation room. If you're a burn victim, infection is a problem, so they'll put you in a positive isolation room. In North America, it's interesting to note, most hospitals, when they design a room, If it's designed positive, it will never be flipped negative. That's kind of sort of changing, because if you go to like Asia and Middle East, if the room can do pressure controls, they'll flip it based on their occupants' needs. They can go positive or negative in the same space. And this is where it gets interesting. They'll put sliding doors, because if it's a positively pressurized room, the doors want to be open inside, not outside. Otherwise, your doors will always be cracked open. And negative is the same way. The door opens outwardly from the space instead of inwardly. The second method of control, which requires a few more pieces of equipment, is direct pressure control. So that now, in addition to the supply valve and the general exhaust valve and the room level controller, we also have to introduce a door switch and a room pressure sensor to give us real-time pressure reading across the space. And this was another space differential pressure reading between the adjacent reference space, typically the hallway, and the room or the zone that we're actually trying to control. In this example, we're showing that the target pressure differential between the control room and the reference hallway is 0.01, which is a typical set point that we see out in the field. In this case, this would be a negatively pressurized space, and we care less about the CFM. We still care about the CFM, but not as much, because here, as soon as my pressure set point is met, what's going to happen, the CFM is going to throttle down to your air change set point and stay there to help you with efficiency. This is kind of a typical lab scenario that you would see. You have your supply valve, your general exhaust valve, your fume hood exhaust, your fume hood, and a snorkel. And then at this point on, most applications is just the quantity increase of said items. So you might have multiple supplies, multiple general exhaust, and multiple fume hoods. It's not unusual for university teaching labs to have 10 or more fume hoods, which will require multiple supplies and sometimes even multiple general exhaust. Some industrial laboratories, they have hundreds of snorkels in different bays, and that in itself is interesting application to be talked about. This is kind of a wiring scenario, all the different points. So you have your exhaust valve brain, which is the UVM as we call it, you'll see. So the UVM represents universal valve module. That's the valve brain. And you can see how the points land on the exhaust, the supply, the fume hood exhaust. This is the fume hood controller, the HMS 1655. This is the room level controller, FMS 2000C. And of course, you got your auxiliaries. You got your room differential pressure sensor. You got your door switch. You got your occupancy sensor if you're using one. You got your reheat valve. You got thermistors, thermostats, temperature sensors, and humidity sensors. So this is the same ingredients used in an application in various different ways to satisfy application requirements. And let's talk about air valves. I get asked a lot is like, why can't I just use VAV dampers in critical environment spaces? And this example is kind of geared to help people understand why not. So good, better, best, right? In the best column is where your Venturis live, and you got your some of the other valves on the market that are geared for these critical environments. And the big difference here is, first of all, speed of the actuator, accuracy of the valve, and most critical environment air valves come with factory mounted controls and factory mounted actuators. You get a packaged solution. And the reason for that packaged solution is so that we can maintain the specs listed above the two, the actuation speed and the accuracy. And the primary differentiator for any critical environment air valve is its ability to do fume hood exhaust. Fume hood exhaust can have lethal corrosive chemicals that can kill you within 24 to 48 hours. And these are not, I'm not making this up. So it's important that the device is reliable and can withstand those environments through the life of the building. I mean, right now I have customers asking me like, hey, can your valve survive 20, 30 years, which is the life of the building? And with a Venturi air valve, I'm comfortable to say, yes, the valve can, but there's some serviceable items like the actuator on the valve. So regular maintenance will allow you to have a airflow valve for the duration of the building. Now, when you come to the industry preference, there's really two camps of specifications that I see. One is a Venturi-based design, and the other one is a blade type based design. There is a lot of debate in this field, and this is going to be my pure opinion, is that there's a place for both of these in the industry. Venturi air valves are great for fume and exhaust. They have no sensors in the airstream, as we will talk about it. They don't care about debris or chemicals. As long as the metal and the coatings on the metal can withstand corrosion resistance, that thing is solid. It's been around for 50 years, and it'll continue to be the go-to standard for fume exhaust and laboratory exhaust air valves. Blade air valves is something that came in the industry about 15 years ago. I think 90, 98, I think Acontrol came out with their vortex shed sensors. And after that, what happened is sensor technology improved, their price dropped, accuracy of actuators and performance actuators increased while the price came down. And now you have sensors and actuators that can repeat the mechanical cone spring performance of a Venturi with a continuous modulating of the actuator. So now, if you ask me, the next 10 years is you're going to see more and more blade style valve specs come on the market because of energy efficiency. The lower operating pressure range or the wider operating pressure range for the blade style air valves becomes a very appealing proposition when designing a lower pressure system out the gate, right? With the Venturis, the floor is 0.3, and that you can't operate the valve lower than that. So when we look at Venturi air valve technology, again, this is a 50-year-old technology. It's been around long enough where this has become a commodity in a ways, and the differentiator becomes the controls that come with the valve and the controls and tying the solution as a whole. The key value proposition of the Venturi air valve is its mechanical cone spring design with this elegant Venturi shape of the shell or the body of the valve. So you can see that the airflow comes in, hits this cone, the air flows around the cone and exits on the other side. And what you get here is a mechanical pressure independent flow control. As your duct static pressure fluctuates on the inlet, that cone spring movement absorbs it and your output remains constant. On a VAV or blade style type valve, you typically have some sort of a flow cross sensor, which is doing a delta P reading, which is converted into a CFM. That CFM is compared to a set point, and if it's below or above, an actuator is commanded to modulate the damper. So there's a continuous PID loop going in there, calculating CFM and adjusting actuator in real time. And we're gonna, as we progress, we're gonna take a look at the value and benefit of both of these technologies. So the first one is the Venturi, and it's important to understand the difference between flow control, which is actuation of the device, commanding it to go to a different CFM set point, and then once it's arrived at that CFM set point, how it maintains that CFM set point without any actuator movement. So what you're seeing right here, this black guy is the actuator. It's modulating the linkage, which is driving the cone shaft and repositioning the cone to a different CFM position. Again, Venturis are position-based control, no sensor in the airstream. Now, once it arrives at its CFM position, what happens is nothing else moves other than the cone spring assembly, and it just slides and glides on that cone shaft based on duct static pressure fluctuations. So if you commanded this valve to 500 CFM and it's within its operating pressure range, regardless of the duct static pressure swings, and we're showing here a full swing from 3 down to 0.6, it will maintain your 500 CFM output, right? Because this is the way this technology works due to this mechanical cone spring configuration. This is a side slice view of the Venturi air valve. So your air is coming in as velocity 1 is hitting the cone, and you see these little gaps around the cone for the air to pass through. That's all there is for the air to pass around this cone. And as more pressure hits it, this cone spring compresses and this gap becomes smaller. Well, that gap is called an annulus, and we're looking at a close-up of it here as the airflow passes through it and the cone spring compresses. The amount of air that it allows to pass through is reduced instantly. Now, this is key when you read the specs and you see instant response. And that's the instant response that they're referring to. They're referring to the cone spring mechanism instantly reacting to duct static pressure fluctuations, absorbing those pressure waves with this cone spring mechanism to reduce the open area of the annulus to allow the air to pass through, hence giving you a constant output on the outlet side of the valve. Now, this is our 8-inch demo valve. And you can see you got your actuator, you got your linkage, you got your position sensor. But more importantly, the black thing is your cone shaft, and you can see the cone and the spring arrangement in there and how it sits in the airstream. If the air were to hit this, you would see this thing get compressed and this cone slide in towards this Venturi. Now, this is the narrowest part of the Venturi body, and these cones typically never go past that point. This is your ideal zero position cone. Now, Venturis, even at a zero position, will have a flow because they're not, there's partially closed and full closed, which have like a rolling lip and a gasket, which seats to give you a pretty much a leak-proof seal. Now, orientation is also key for Venturi air valve. That's another kind of backdraw, you could say, of this technology where the cone spring assembly is not impervious to gravity. And at the time of selecting equipment, you should know whether it's going to be installed in an upflow or a downflow position or a horizontal position, because that's part of the configuration of the device that you'd have to order. And in the factory, we will calibrate it vertical up, vertical down, or horizontal, and it cannot be replaced in the field. We had a customer that ordered $50,000 worth of air valves only to realize he ordered the wrong orientation. Don't do that. Not fun for anyone. And this is pointing the correct way. So you can notice the Venturi shape right here. This is the money. That little shape is on the inlet side of the valve. The equally tapered shape is the outlet side. Now, Venturi-based, position-based flow control requires some factory characterization in order to define what the CFMs are at the different positions. The industry standard is 7 positions and 7 pressures at each of those positions, giving you a total of 49 data positions, which are then linearized and dumped into our valve brain. And the way you would interface with it is with a simple scale 0-10 in, 0-10 out. That calibration is done at our factory in Norcross on a NIST traceable setup, which has plus or minus 5% accuracy. It verifies pressure independence, does a 4-9-point calibration for each air valve. That same CFM to volt data is attached to each valve. It's loaded in its brain, and it's stored at the factory in case there's some event in the field where you need to replace the curves for the device. Now, there are the 3 C's that are kind of used in this space, and it's important that we all understand them, and that's calibration, characterization, and configuration. Calibration is us taking our equipment and calibrating it so it meets our published spec. Characterization is what we do on each individual air valve to capture its unique flow data sets. And you'll see that 2 identical valves will have minor flow deviations by 3 to 4 CFM, but still within plus or minus 5 CFM, just because of different metal configurations that are beyond our ability to control. And finally, configuration is that something that's done in the field. Now, when you're talking about these scenarios, I hear these 3 words used interchangeably, which no doubt will cause confusion. So it's important to get those understood as we proceed further. So when we look at factory characterization, this is what every single valve that we produce comes with. It comes with a chart showing that at 0 position, it maintained its flow throughout its entire pressure range. And all the way up to 100%, it shows that it maintained its CFM regardless of duct static pressure swings, plus or minus 5%. That data gets linearized and put into a simple lookup table inside of our UVM PCBA here, which is mounted on each valve. That's our valve brain. And it's very simple lookup table, meaning here's the position, here's the feedback, and here's the CFM. And the same information is basically found on the labels attached to each valve. So what are the benefits of using our valves with a universal valve module? Well, to me, it's one of freedom to the end customer. Before the UVM, we introduced the UVM, customers were locked into a turnkey solution. Our air valves and our controls and our service and our installers, et cetera, et cetera. So you really couldn't do anything unless you bought the whole kit and caboodle. What we did, we said, well, let's piece it out. If you just need the air valves, because you already have controls platform that you're versed in, here's a agnostic solution for you to have precision airflow control in your spaces. And what I'm trying to do is I'm trying to commoditize the Venturi air valves so that anyone and everyone can command and control these devices with a simple 010 in, 010 out command and control signal. And what that does, again, it gives the owner the freedom and the independence to command and control his own equipment without having to call somebody else to come in there and make those setting adjustments for them. Again, this is a logic layout of what the UVM does. It's fairly basic. The tables is what we populate in the factory. So we know for this device, this position at this pressure is equal to this CFM. And that gets linearized to a simple 010 in request command signal for your CFM and a 010 feedback CFM signal. There is a UVM configuration tool that is required to do any kind of field K-factor setting, adjustments, or pull some data, or we're troubleshooting, manual overrides, et cetera, et cetera. That tool comes, it's a free tool, comes installed on your PC. You get a USB to RS-45 cable, and it connects to the side of our enclosure on the valve. And at that point, you can communicate with the device and perform any sequence of operations that you'd like. Another great thing about the UVM is that if you daisy chain all of these on our RS-45 pseudo Modbus standalone network, you can get up to 15 valves to sum their CFMs into a single master CFM. This is very valuable when you have a room where you have 15 air valves and you're running out of IOs on the room level controls. Here I can take my total exhaust and my total supply, and I just have 2 sets of IOs now to take my total supply, total exhaust, and balance the room. Neat little feature. And when you wire them daisy chain, you only need to connect to one so that you can then command and control any other ones through this daisy chain setup. So finally, the advantages of the UVM is increased owner independence, lower acquisition costs, simplified integration, reduced maintenance. This is all done with the end user in mind and how they want to command and control their spaces without having to get third parties involved when simple settings need to be made. Performance highlights of the Venturi air valves. So when we look at the flow, blade style valves have this inherent feature where just as you crack it on the blade style, there's a little back pressure built up. So you get a surge of CFM coming out of it from like a 0 to 10% open. Whereas with the Venturis, it's the opposite. On the lower end, we have this very nice gradual control that really gives us a nice stable airflow metering capabilities. Whereas at the low end with the blade style valve, that's still a challenge, and various valves on the market are working to get around this phenomenon. So that's the advantage of the Venturi, especially when it comes to these low-end controls for like vivariums, where you need very low flows for multiple small little animal containments. Lastly, inlet sensitivity, also known as straight duct requirements. If you're using the delta P reading, most of us understand that air is like water and it settles and it's turbulent. So you'll see that there's some straight duct requirements, which sometimes becomes prohibitive from a design standpoint of view. And that's where Venturi, again, has an advantage over sensor-based digital devices that require a fairly laminar way to read an average pressure of the duct to get you a correct CFM reading. And basically, these slides are showing those variables in effect when you have duct bends. Those said variables can be extrapolated to a margin of error, which of course can be managed and maintained, but it shows that there's a level of controls and accuracy that needs to be managed and contained when you're using devices that require straight duct airflows. Now, Venturis, that's the beauty of the technology. They don't care, right? As long as you're within the operating pressure range, whatever that swing inside of it is, that cone spring assembly will do what it's supposed to do. But the main reason you want to use a Venturi is this. So this was a hospital in Boston that in 1 year's time, this is how much lint accumulated from a single patient room. And it's because of all the linen changes. That is just general exhaust. It's not even fume hood exhaust, right? So as this flow probe starts to foul up, your CFM reading starts to drop. So the valve starts opening, thinking it needs more air, and eventually reaches a full open condition and a 0 CFM reading. And that's when the room goes into alarm and everybody starts freaking out, going, it's unsafe, we need to shut it down, call the experts. What do we need to do? Well, that's when you climb up the ladder, cut the ductwork open, clean out the sensor. And if you're smart, you're going to put a permanent clean out door unless you're going to change the airflow control device, right? Same with these two pitot tubes in here, right? This is just regular dust and debris that you find in general exhaust, and it's going to foul up your sensors in the airstream. I had a project in Latin America where we had this very same conversation. I showed them these very same pictures, and they went for the lower upfront cost of VAV boxes. And in a year, the owner said, you have to fix this because I can't have people going in there and doing maintenance, shutting down rooms, cutting into ductwork, et cetera, because then I got to rebalance the room afterwards each and every time. Here's another example of fume hood exhaust that failed to pass the ASHRAE 110 test. I don't know what they do in fume hoods, but I wouldn't put my hands in there, especially if they're able to suck in all these tissues and whatnots to foul up the valves to that extreme. And if you've got valves that have sensors in the airstream, that's going to present another challenge. That's why some of the valves in the market critical environments come standard with a clean out door, because they understand that one tissue or enough buildup on their sensors in the airstream is going to render this device useless, is going to throw up a no flow alarm, which is going to trigger a room level controller to go, hey, something's wrong. I'm going to throw the room in alarm. And then you got a situation where you got to either evacuate a room or decommission a room and then get somebody else to come in here and try to fix the problem. Finally, we have a Venturi valve upgrade kit. This is geared for old Venturis that the cone spring assembly and the valve body is good and it's still doing what it's supposed to do. But the actuator is pneumatic, the controls are legacy, and they're not integrating with your building automation. And you have a space where you don't want to do a capital expense and introduce new valves. So you can use an upgrade kit, which comes out of your maintenance budget. So you can just do an in-field retrofit without having to without needing to get into the ductwork. And the kit is fairly simple. What you're seeing here is a Phoenix air valve where we remove their controls and their actuator, and we add our linkage, our position sensor, and our actuator with the UVM. Then we look at their label and their flows to voltage, and we either enter those into the UVM manually or we do an in-field calibration to populate that lookup table that we discussed before. And what this allows you to do is now have digital control, 010 in, 010 out, and that space can now be brought into your building automation umbrella. This is a common theme that we see with universities where they're doing building automation campus-wide rollout, and they're running into these labs with legacy controls. They don't have the budgets to do all new equipment. So this becomes a very appealing selling proposition to them if they can just use a maintenance budget to do these kinds of upgrades. So that's then for the air valves. Now we're going to get into controllers and monitors. These are kind of like your brains and your eyes and ears in a space. And the first one is the FMS 2000C room pressure controller. But it's a lot more than just room pressure controls. We call it the critical environment controller because it does humidity, temperature, changes per hour, got multiple alarm conditions and occupancy modes, et cetera, et cetera, et cetera. Now, this is the display. You got your controller where your wiring termination is in, the CPU in this box here, and this is your room differential pressure sensor. So when you buy an FMS 2000C, this is what you're going to get. You're going to get a display, you're going to get a controller where all your wires will terminate, and you're going to have a remote pressure sensor, which we typically recommend you mount above the door facing the hallway to the entrance of the room. And the reason we do that is so that you can service it or any other equipment without having to be entering the space. Secondly, our CMS 2000 central monitoring station, great for nurses' station. If they got 8 different rooms, they're trying to monitor the pressure, occupancy, or whatnot. One little display, and if there's an alarm condition down another ward or a couple of doors away, they don't have to run and look. They can look at this and see exactly which room it is and make their decision accordingly. That CMS, by the way, is also in the specs. They say you got to have a nurse's station. Our fume hood controller, again, working to upgrade this to our 2000 display, but it comes with the fume hood controller, same hardware as the room level, different software. It comes with our sash position sensor, comes with a sidewall differential pressure sensor, and an optional occupancy sensor. And fume hoods are really the kind of, to me, they are the center point of critical environments. They are the most critical piece of HVAC equipment in a lab. They are the primary source of contaminants. And it's interesting that the #1 source of all contaminants in laboratories are the users, because they're the ones coming to cabinets and pulling the chemicals and mixing them, right? So every time there's people in a space where there's labs and they're doing experiments, contamination rates go up, and that's why air change rates go up, et cetera, et cetera. And there's 2 modes of operation for fume hoods. There's the constant volume, and then there's the variable air volume fume hoods. And that's what we're showing here. On a variable air volume fume hood, as the sash opens, more CFM is being exhausted. As the sash closes, less CFM is being exhausted. Pretty basic stuff. Well, let's keep going and see how far that holds. Some people or some companies offer what we call open loop controls, aka sash only fume hood controls. What that means is I'm not measuring air or pressure or velocity in real time. I'm calculating it only based on my sash position, my opening area, and I'm just trusting that there's air in the system. I'm trusting that the valve is doing what it's supposed to be doing so that my calculated value is correct. Interesting. Is there a better way to ensure safety other than calculations? Well, this is where we like to introduce the sidewall sensor, because what happens if the fan's off, right? And you're just calculating and you're not measuring, you're still going to read as it's safe. Yeah, I'm still at 100 feet per minute, even though the fan's off. Now, some competitors will put differential pressure switches across their valves to trigger an alarm of a low flow condition where there's not sufficient air. And that's one way to do it. But that does not account for fume hood loading in the workspace, Bunsen burners, big ovens, racks with beakers and other equipment. So you really want something that will, in real time, tell you the fume hood conditions and help you throttle the exhaust on that fume hood in order to maintain a safe face velocity. So in addition to sash position sensor, we also highly recommend using the sidewall differential pressure transducer or sidewall sensor, which is what we use to measure the conditions inside of the fume hood workspace real time. This gives us a closed loop control sequence for fume hoods. This ensures safety, reliability, and efficiency. So fume hoods, and this is kind of a zoom out. I can spend a day talking about fume hoods, but there's two different systems that we need to think about, right? When you approach a lab with fume hoods in there, first question I would be asking, okay, is it a variable air volume lab with variable air volume fume hoods, or is it a constant air volume lab with fume hoods? Because the two are very different animals. They're designed for the same thing, safety, but one is not equal to the other in different regards. So while variable air volume systems allows you to throttle the exhaust and throttle it down in unoccupied or unused modes, the sequence of operations in VAV applications is a lot more complex because you need to define occupancy, you need to define setback modes for low air changes and occupied air changes, and potentially even contaminant levels if we're doing air quality type metrics. Now, when it comes to constant air volume systems, I call it a set it and forget it design, because the moment you just get all your CFMs right, you lock it in place and you forget it. What this does, it simplifies it on the design front end, but it locks the users into a fixed exhaust, fixed cost of running that lab, with very few opportunities of how to increase the efficiency so they can decrease their utility bills. So what is a fume hood? A fume hood is just an enclosure to capture and contain harmful vapors, chemicals, has no filtration, it's single pass air in the lab and it's right out the building. Typical fume hood in the US uses 3.5 times as much energy as a home. So that's one fume hood. Here in Georgia Tech, they have one building that last I heard, its annual electricity bill for running all those exhaust fume hood stacks on the roof was in the vicinity of $50 million. So when we say that these things eat a lot of air, oh yes, that's why I say they are the most HVAC hungry piece of equipment in the lab. Ironically, what's really frustrating is that they're sold as lab furniture and are specified by architects. And the HVAC guys, we get basically no say-so in this. When fume hoods are sold in spec, the first thing that the lab folks got to do is put controls on them. That's where our HMS 1655 comes in. And then once you have air in the room, you have controls on the fume hood, these fume hoods need to go through a commissioning process. And that commissioning process takes form of an ASHRAE 110 test. Now, fume hood safety was typically defined as face velocity, and the standard, still to this day, people could argue it was 100 feet per minute. Well, in 2012, ANSI Z19.5 lab standard comes out and says face velocity alone is an inadequate indicator of fume hood performance. There is no direct statistical correlation between fume hood's average face velocity and the containment levels provided by the fume hood. Boom. Right? Suddenly everyone's like, oh my God, so how do we know if the fume hood is safe if it's not face velocity? Well, it's containment, right? If it's containing, it's safe. If it's not containing, it's not safe. Ironically, the best measure for fume hood containment is back to face velocity, which is feet per minute. And that's why the ASHRAE 110 test is the standard 3-part test that includes a face velocity profile, where we're getting some readings on what the face velocity is. Is it at its design face velocity? Yes, it is. Okay. Now we're going to run some smoke around the perimeters of the fume hood and see, is that smoke actually being drawn into the fume hood? Then they're going to run some smoke inside of the fume hood to see if that smoke is actually escaping the fume hood. And lastly, and most famously, is what they do a tracer gas test, which is sulfur hexafluoride. You can see the little flow gauge in the cabinet here and a little diffuser they have in here. And this is Simon, our friendly fume hood dummy tester, with a little probe in his mouth that represents the user's breathing area. And the allowable limit is 0.05 parts per million. Right? If you can't contain at whatever face velocity is, right, you have a problem. You won't pass commissioning, and you won't be able to release the fume hood for occupant use. Now, here's the interesting thing, right? Oh, benefits of stable vortex. Hold on, let me jump one ahead right here. So when we talk about fume hoods started as fireplaces. Fireplaces were the original fume hoods, and I'm sure everyone's encountered a fireplace that had a spill and a little bit of smoke came out, but once it got going, the heat kind of took over and pushed through the pressure, temperature, load of the chimney, and it kind of started exhausting properly. The number one risk in the industry today is not some one big event in the fume hood, big spill. It's micro spills in the breathing area of the fume hood users who use it every day. So this example here of this lady mixing whatever chemical she's mixing, and she's doing it on a regular basis, we're not worried about one big spill because that can happen, just user error. But if the equipment's not properly balanced and she's getting a small little microdose of this every day, there's been cases where people have sued the building owners for chronic illnesses, and the case went in their favor, meaning the building owners lost because they couldn't prove that their fumes were safe. No monitoring, no controls, nothing. And I believe that, based on a study that came out of Sweden, is that people who use fumes on a regular live by about 10 years less than regular population, which tells me that these micro spills are regular and a common occurrence in majority of fume hoods in the industry today because of just slow adoption of these, call it closed loop fume hood controls, where we're actually monitoring and alarming when we detect an unsafe condition. Having said that, what defines a safe condition? How do we ensure that a safer, better way of running fume hood? And one of those ways is a stable vortex. So it's pretty much impossible to get laminar airflow inside of the workspace of the fume hood because all the Bunsen burners, grills that they put in there to hang all the equipments and so on. And even the geometry of the hood was, in some of these traditional hoods, was never really intended for laminar or cohesive airflow patterns to ensure containment because it was made by lab furniture people. They didn't know about air. So FlowSafe was born out of one gentleman's twin brother dying at a fume hood accident, and him being an engineer, he looked at it real hard and he came with a very interesting proposition. Said, well, if you can't get laminar flow, the next best thing is a stable rotating air pattern which simultaneously pulls in fresh air and simultaneously exhausts any contaminants in that workspace. And by just changing the geometry of the hood and modulating these dynamic baffles, we are able to contain and ensure that that vortex is always present and spinning, and we can alarm and warn people when they're approaching those conditions where that vortex would break down or something would happen to trigger unsafe condition. Again, showing a little bit when the sash is closed, that vortex does the sound and descend and touch the work surface of the fume hood. It does expand across the workspace. And as you lift the sash, it does raise up and become smaller in the area. These are fairly evident in smoke tests. If you ever see one in person, as you raise and lower the sash, that vortex kind of tracks the fume hood sash opening. And the advantage here is that I can get the same levels of safety at 60 feet per minute versus 100 feet per minute. Conventional fume hoods were about 100 feet per minute. The stable Vortex 2 fume hood passed ASHRAE 110 containment test around 53 feet per minute. We don't recommend that. We say the lowest you should go is about 60 feet per minute. These are our dynamic baffles and inside of the workspace. We have a combination sash that's both horizontal and vertical sash panes. Comes with a vortex management system display for all your alarm and set point conditions. This is our sensor that we use for sidewall sensing of that vortex. And lastly, again, a lot of this stuff is not only CFD verified, it's tested and verified through the ASHRAE 110 testing. Again, I can't stress enough how important the ASHRAE 110 test is for fume hood safety determination. Now, one thing also to consider that sometimes replacing fume hoods is a costly project. So a fume hood is a metal superstructure, which is this metal frame that's typically attached to the walls or fume hoods next around it and sits on top of cabinetry and work surfaces. So what we offer also is a conversion kit where you can keep all your sheet metal in place, but just the internal baffles and the geometry of the sash is what needs to be replaced. In this specific project, they had asbestos in the walls, and if they were to pull out this fume hood, they would have to do asbestos remediation, which was a showstopper for them from a financial standpoint. So a conversion kit became a very appealing solution where they can go in and retrofit 50 fume hoods without having to do asbestos remediation because they never cut into the walls. So finally, kind of to summarize here in the last couple of notes, the advantage of our solution is that we can provide turnkey solution or individual equipment for whatever little piece you need. Now you can piecemeal it together or you can get one system that ties together. We are BAS agnostic. What that means, we talk BACnet MSTP. If there's an existing controls platform you want to use, our equipment seamlessly ties into that. BAS agnostic fume hood controls, that's important. BACnet solution, like I said, BACnet MSTP. Retrofit kits available for both Venturis and fume hoods, and again, a high efficiency fume hood to help tie the lab solution together. And with that, I'm going to pause and take any questions if there's any.
Thank you, Auri. That is a ton of information, and I hope everyone knows that, you know, we have Auri to help us and Titus to help us for your next lab application or anything requiring critical control and using Venturi valves. So we'll pause here for a few minutes and feel free to ask any questions in the chat. For those of you that have other things you got to get to at the rest of the day, thanks for joining us, and make sure to join us next week when we do the other part of the lab system with our GreenHeck lab vans, our Vector series. So with that, thank you, and we'll stick around here another minute or two. Thank you, everyone.